So, hello everyone. My name is Romain. I'm an independent consultant in the field of data and machine learning engineering. And today we're going to talk about why you should not use, or maybe you can use something else than Spark for data lakehouse workflows. Just so I get a heads up, who knows what a lakehouse is? Just, okay, so half the audience, so great, thank you. So, just in case, sorry. Okay, it's working, perfect. So just in case for everyone to get on the same track, I'm gonna do a quick recap on what is a data lakehouse. So this is a new term that has been happening since the past 10 years or so. So basically the idea is to bridge the gap between data lakes and data warehouses. So on one hand, the idea is to get the flexibility of data lakes. So basically, you can throw any data into your file storage or object storage or whatever you're using for your data lake. But at the same time, you can still keep the strong benefits of data warehouses. So basically, you get ACID guarantees. And so everything that makes your data more consistent and more usable for people to explore and get started with. Also, again, you keep the idea of data lakes, such as having some cost-effective storage and compute where you can decouple them and scale them separately. So you can have your storage staying there for days, months, years, and we don't pay a few cents or a few euros or dollars per year, and you just pay for compute when you need it, compared to data warehouses where it gets expensive really quick because basically you're paying for idle servers. And so all this blah blah to get to the point that now that we have open table formats. So you may have heard from the data giant, Databricks, Iceberg, Snowflake, etc. Some formats such as Delta Lake. This one has been created by Databricks, Icebergs from Netflix, Hoodie from Uber, or the recent one, Duck Lake from DuckDB. This one is pretty new. It's been released this year, actually. So it's still very early, but it's very promising. So we have all those formats, and they have been designed to be worked with Spark at the beginning. So just basically, this is an illustration from Databricks itself, showing you how we got there since the 80s. So from the 80s, with the strict rigidity of data warehouses to the flexibility of data lakes in the 2010s era, where we basically would have to throw any data and we did not know what to do with it, and it would become very easily data swamps. And now we try to have a more mature approach, which is basically combining the best of both worlds. Okay, I hope everyone got the idea. So, quick recap on the features that makes up a data lakehouse. So you get the performance and cost benefits of data lakes. So basically scalable storage and compute and independent scaling, and the flexibility of putting every data you want inside of it. But also on the other hand, now you have the ability to add ACID guarantees. So basically been making sure the data is not corrupted in between workflows if you have failed jobs and stuff like this. And schema enforcement. So one of the things that would make up for data swamps in the past from data lakes is that there was no schema. People would throw CSVs and JSON with any data schema, and you would have to basically do what we used to call schema on read. So now we try to go back as much as possible to what we call schema on write. So basically you enforce some schema, but you let it evolve through time if you can. Sorry, one last point. Because of all these added guarantees on top of data lakes, you now have some more features, such as what we call time travel. Time travel allows you to go back in time into your tables. So basically, you can go back in time into your data which is pretty good. It allows you, for instance, to perform reproducible machine learning experiments, debug, whatever you can come up with. It's basically you're the Marty McFly of data engineering, if you want. And then you got snapshots. So basically think Git branches onto your data, and you get the idea. So what a data lakehouse format looks like, I will take the example of Delta because it's one of the easiest to get started with. But this one is very portable also. I really like it. So the idea is that a data lakehouse table is just a folder on a storage. You have like a transactional log inside. Here it's a Delta log folder, and you got JSON files. And all those JSON files basically contain transactions. And then you have packet files. So it's a combination between some transactional log in JSON format and packet files. For those who don't know what packet is, think CSV, but binary, colon-oriented, with compression, and that's it. And data type, sorry, yeah. So yeah, this is what a lakehouse table look like at the bare minimum. It can have way more stuff around. For those who may have heard of Iceberg and work with icebergs, it's way more complicated than that. But just an example to see what we are dealing with. And so, no, the big question, why not Spark? So like I said, all those lakehouse table formats were initially developed with Spark in mind because they were targeting big data. Everyone knows Spark is targeting big data. It's able to handle massive workloads, but to get the benefit of Spark, basically under 100 gigabits of data, not might be the right tool for the job. So basically, if you ever try to perform some complex lakehouse workloads and develop them locally with the team, especially if you work with data scientists who are not accustomed to Spark and those complex data engineering practices, and get them to develop locally on their laptop with Spark and Delta, and there is no open source catalog except for Unity, but whatever. And so it's very cumbersome to set up. It's the cost of running on your laptop is very high. And so yeah, that's one of the use cases where Spark might not be the best tool for the job, but also people who do not have big data, basically, most companies, like I said, most companies have medium-scale data, so under 100 gigabytes of data to process, and even then, usually not some long-running data pipeline, but some inference pipeline or whatever is gonna just process a few megabytes or hundreds of megabytes of data at a time. So Spark might be overkill. But don't get me wrong, I'm not a Spark hater. I like Spark when it's useful for me. Not in this case. So now we get to the good stuff. In 2025, we have some alternatives. So how to get started with Python without Spark to manipulate data lakehouses. So I've taken the liberty of listing the current state of things. If I made a mistake, please tell me. For the major format of lakehouse tables. So basically, you have Delta, Iceberg, Hoodie, and Duck Lake. You have native libraries for Delta, Iceberg, and Hoodie. They are taking a form of a Python package. Usually, they are implemented in Rust, and you get the binding, basically. So you get still some performance optimization. It's very well written. Polars, of course, handle Delta and Iceberg seamlessly, and DuckDB is the one to support Duck Lake because it's the same team behind it, of course. However, for Delta and Iceberg, you only have some partial support, such as only read operation. You got no time travel for now, even though there are open PRs that are getting resolved recently. But yeah, still. Okay, let's get some hands-on examples, some code snippets. I'm going to show you on how to get started, in this case, with the Delta Lake Python library. This one used to be called Delta RS, for Delta Rust, if you will. But no, the real name, if you do pip install, it's pip install Delta Lake. So we're going to see how to create tables and write data, perform some merge operation, inspect the history, and perform some time travel. All that, pure Python, no Spark clustering included. So it's really easy to get started. You use the Delta Lake library, like I said. So basically, you do have to define something, such as the table URI. So the URI supported are either local storage, so basically you give an absolute or relative path on your local machine, or a remote table on Amazon S3, Azure DLS, or GCS, basically. These are the 3 backend supported for now. And of course, you can always give credentials using the storage option right there. For now, it's none, because in the example, I take some local storage example, but you get the idea. And then you can specify a data schema that you want. You know, if you know in advance how the data will look like in your table, you can specify it. So it reminds us of the good old SQL way of creating tables, but still, now we're using some basic example here. We're gonna store some weather forecast, and that's it. And we can happen also some metadata, such as the name and description of the table, but this is just purely human readable metadata that is used by the user or the analyst. Okay, just this operation creates this folder. This folder, like I said, it contains the Delta log folder, which contains itself the transaction log. We can see there is only one single JSON file, because basically this is the transaction data for the table creation, as simple as it is. So there's no Parquet files, because the table is empty, so there's no need to store data. Let's inspect the table metadata. We can retrieve all the metadata we previously set on the example, to the exception of a few things. There is an automatic ID that has been created for us. There is some creation timestamp. And also, you can see there is a partition columns list here. We have not specified some partitions in the example, but you can do that if you know in advance that you are going to have some partitioning benefits for your data set. You can just pre-partition the table in the metadata. And it will split up your Parquet files like in the initial screenshot I've shown at the beginning. And that's it for the metadata. We can inspect the schema of the table we have created, and it's compatible with Arrow. So everything is compatible with Arrow with these libraries, so which is great because it allows you to have some interoperability with most of the data libraries that we use nowadays. So here, nothing fancy, it's just the schema we have defined is just compatible with Arrow types. And now, finally, we can write some data to our table. So here I will take a really bare-bone example, just to get the idea. We define a data frame. It can be pandas, polars, or it can be an Arrow table, or an Arrow data set, actually. And you just call the write data function, which is taking, again, the table URI, some storage options, and the data frame. And one interesting thing to notice is the mode. We have the choice here to define, exactly as with Spark, the mode on how to write the data to the table. So either we append the data, so basically you just append the rows in the table, and you can have duplicates if some rows are overlapping. And also you can use the overwrite mode. Basically it will overwrite all the rows in the table, but you can still get back to it with time travel. So nothing is ever deleted. This is all immutable storage. So after this operation, we now have a new Parquet file. Yay! You can see it here. It's written with some UID. There is a new transaction data that has been created, the 1.json. And so, yeah, this is the changes are tracked. We can do some fancier operation in a merge. Like here, we do retrieve some new weather forecast. Some values have been updated in terms of temperature, but there are some overlap in terms of timestamp and city, and we can just merge them. So there is a merge utility in the Delta Lake library. So you instantiate a delta table, gives you the reference, and then you use the merge operator. You define some predicates, so which rows should be matched in the upsert. So upsert is update or insert. So when it's matching, I want to update the rows. So then I can define how to update it. So here I want just to update the column temperature with the source one, which is the new data frame. And when it's not matched, so basically it's new data. So I want to insert it. So I say when not match, insert. And here I specify how to insert the data, which data to insert and when. And I execute it, and basically it gives you that. And now we have 3 packet files instead of 2. Why is that? So we still have a new transaction. Here it's the normal order, but we have 3 packet files and not just 2. Let's see why. At the top is the first packet file that was created at the first happen operation. So basically you get all the initial data with the initial temperature values. The second packet files is the one in the mystery. Basically, this is the update operator. Rows that have been matched in the initial state and that should have been updated and was updated actually. There, basically, it has duplicated the file in Parquet and updated the values. And then it has created a new Parquet file with only the new rows appended, basically, in the upsert operation. And that's it. So this feature might be overkill, but this is what gets you immutable reads for concurrent readers and writers, basically, and ACID transaction. So you always have a trade-off in this kind of thing. So, yeah. So then, yeah, we can read the table, okay? I just, again, an instantiate a delta table. I can point it to a URI. I can specify dynamically the version. I'm not doing it here. And you can see the default version is the latest one, of course, because this is the most sensible thing to do. You load the latest version by default, and then you can export it to here, pandas, but you can export it to polars. You can explore it in Data Fusion or whatever you want. Okay, just going through a quick overview of the in-story inspection of tables. So basically, this is just reading the transaction log, the JSON file, if you want. So basically, here we have the create table operation that was recorded, then the write operation in happen mode. You can see it here, and you got some statistics about the execution times, the number of files added, etc., etc. And the merge operation, which is way bigger because it needs more metadata to be recorded properly, especially like how many rows were deleted previously, or how many files were deleted, etc. When it says deleted, it's marked for deletion. It's not deleted like we've seen. It's immutable by default. Okay, now we can be Marty McFly of data engineering and do some time travel. So if I take back my table that I've instantiated previously, I can load the version by version number. So if I know the version number, I can just load as version. And here I'm doing it in ascending order. So version 0, you can see it was the initial empty table, the version 1 with the initial temperature values, and version 2 with the updated temperature values plus the new rows appended. That's it. Nothing magic. You can do that also by timestamp, and this is where it gets more interesting, especially for machine learning experiments where you want to have reproducible results. Like, okay, I want the data from last month, and I want to be able to reproduce exactly the same experiment. You can just load as timestamp, get the timestamp, and that's it. Okay, I'm not doing it here because it's a quick snippet. Yeah. Okay, now how can we use this and combine it with a crazy fast query engine in the name of DuckDB? Someone talked about DuckDB previously this afternoon, so you already got a taste of DuckDB today. Let's do some more, basically. So first of all, DuckDB, you can use it either from the CLI, which has nothing to do with Python, or from the Python binding. Just for people using DuckDB from a CLI, there is the native support of delta table and, okay, my pointer is gone, whatever. So you can just perform some select from delta scan and give a URI, same as we did in Python, and it will load you the table. But where it gets interesting is the interoperability with Delta Lake. So basically, like I said, DuckDB only performs read operation on delta tables or iceberg table. There's no writes, and also it cannot do time travel for now. It will come in the near future, but still, for now, if you want to explore that and you want to perform time travel, you have to go through some interoperability between the Delta Lake Python library. You create a PyArrow dataset, not a arrow table, because the arrow dataset is a lazy one. So basically, it will hold up the references onto only the expected packet files that are needed to be read for the given version of the table. And then you register it as a view or as a table in DuckDB, and basically you can query it like any table in DuckDB. And it will use the arrow dataset underneath to perform the queries efficiently. So this pattern, I've used that successfully many times. It's very powerful. You get all the benefits of DuckDB, which is crazy fast multi-threading on a single node. You can go up to almost 100 gigabytes on a commodity laptop. It's crazy. Okay, now I got a few minutes left. All these bases I've shown you, I've put that into a new open source software I've basically started this year, which is named Lake Tower. So basically, Lake Tower came from personal and professional needs, where every day data scientists and data engineering teams work together and industrialize solutions, and one of them was working on Databricks. On Databricks, it's very hard to our knowledge at least, to develop workloads efficiently, fast, on your laptop, and then being confident it will run properly on Databricks, because the whole thing is supposed to be happening in the cloud. We are software engineers, we want to have best practices, and also the data science crowd I work with are not really accustomed to DuckDB, for instance. So I could not throw DuckDB at them and say, okay, you can just develop with Spark locally and just inspect your delta tables and your experiment locally with DuckDB. They have to know SQL, the DuckDB SQL dialect, etc. So basically, I've took the opportunity also for me to learn more about those alternatives to Spark for Lakehouse format and DuckDB also, and I built Lake Tower. So yeah, I can quickly show you if, I don't know, sorry. I don't know where the mouse is. Okay, it's there, okay. So it's available on GitHub, Data LPI, which is the name of my company, /Lake Tower, and it looks like this. So basically, with Lake Tower, oh, nice, demo effect, because I know why, because here you go. Okay, so with Lake Tower, just simply define a YAML file, which is basically your data catalog, static data catalog for now. You define where to look for your delta table. here it's only support Delta for now. More will come in the future. And so basically once you have that, I cannot see anything, sorry. You have a CLI to inspect or query your table, whatever. You can use UVX to get started. It's, oh, crap. I will fill the blanks. So you can use UVX to get started very quickly. So UVX Lake Tower, you give a config file and you can inspect the table, query the history, the metadata, do some time travel and do some queries with DuckDB just at the comfort of your CLI. But the more interesting part is the web application, because if your crowd wants something easier to get started with, okay, sorry, holding the mic isn't easy also. So you basically get exact same feature as the CLI in terms of a web application. You got everything that we've been doing with the Python Data Lake package and DuckDB. So you can look up your table, you can go back in time, you can, I'm not seeing anything, sorry. You can query the history, you can import some data in your table. And something that is usually appreciated is this one. You can predefine some queries in your metadata with some parameters, and so people can use basically the interface, like a form or whatever, onto your Lakehouse tables, and so you get some conveniency in using Lakehouse tables. Okay, this is very early, very drafty. Let me go back to the presentation. So, okay. So, yeah. Okay. So, to finish, to conclude, start simple, basically. You may need Spark, but maybe not at the beginning of a project, maybe not working locally. If you can, try the Python tools. They are available. Everything is open source. Everything is free to use. So why not start without Spark someday? Because if you have just to update 3 rows in a table, I mean, spinning up a JVM and a Spark cluster might be overkill. But maybe that's just me.
Are there any questions?
Thank you. One thing I find difficult with Data Lakehouse, data frame, is the schema, that it's often like put in strings and you change it somewhere, you forget to change it in another place. Do we have tools to manage the schema maybe in a static way and evolve it the same way that we have like ORMs and migration tool for databases?
That's an excellent question. Thank you. To my knowledge, except from DBT, that you may be able to do something with that, there's none, basically. And basically, people struggle with versioning SQL files, or because it depends on your query engine, but you version SQL files with your data migration of schema, basically. That's what I do, and that's it. Even the data giant do not provide any solution to that. I think there is one open source project for data type migration on Data Lake. I don't remember the name, but it has limited support for Lakehouse tables. So, yeah. Yeah.
Do you have a go-to strategy to whenever you need to deploy, for instance, Delta Lake on the cloud to spin up a VM, have it do the ingestion and the definition of table and then shut it down?
Not sure I understand the question, but basically, do you have like some quick startup strategy on how to make use of that? Basically, okay, in the cloud. Yes. Okay. First, you need an object storage, of course. And then, so basically, you can do anything. Those are open table formats. You can use any object storage you want. You can basically just give URIs and credentials on where to store and read and write the tables, basically. And then you can use any compute you want.
Well,
It depends on the workloads, basically. I like containers as a service because it's agnostic. You can run your container on your laptop. You can deploy it as serverless. You can do anything. If you are accustomed to Databricks, you can use Databricks workflows but this is tied to Spark in a way sometimes, even though they do have some serverless offering right now, but it's very limited in what you can do with it. Any compute, basically, but I like container-based things, so yeah.
One last question.
Yeah, thanks. Interesting talk. Just a question about the openness, right? So, like, I've looked at Delta Lake and I've seen deletion vectors is not quite there, and and you're writing in Databricks, you can't read in Delta RS. Databricks are not supporting Delta RS as far as I'm aware. It's an open source project. What's your take in terms of the iceberg Delta kind of competition at the moment? And if I'm to bet on something, what should I be betting on? And then what's your take also on open compute? This is called Open Lakehouse, but Databricks closed the compute. Snowflake closed the compute. They do not want you running open compute.
Yeah, that's a good one. Thank you. So first of all, these are open table formats. You can use them without Snowflake or Databricks or Azure or whatever. To my knowledge, and I'm trying things as we speak, with Databricks, you can use, for instance, Delta RS right now, because they do have open some temporary table credential API in Unity catalog that you can query. So basically for ADLS, you will get a limited SAS token to the storage and you can hook up. It's still like a work in progress. This is particularly effective if you are not using Spark cluster and only doing serverless, because it's very lightweight then. But then, yeah, on the openness, I don't know if I would have to bet on something, Duck Lake. Maybe. This is maybe the more open of all. The company behind it makes some very strong assessment about that. Even the cataloging format, because Duck Lake is a bit different. They're using like a SQL relational database for the cataloging. It's open, the schema is open. Unity catalog, you do have to spin up a JVM server just to get it. I don't like it. So if I would have to bet on something, it's Duck Lake for the future, but it's still very early. Yeah, this is all very experimental. I'm just providing some leads on how to get alternative, unfortunately.
If there are any other questions, please take it to the coffee break. And let's thank Romain once again.
Thank you, everyone.